Welcome back. Today it's October the 23rd, and we're going to continue here on chapter 8. Last time, when we were talking about this practice homework, we stopped right here at problem number 5. We were talking about the coumarin structure. And so let's develop this problem. It says coumarin is an important natural flavoring. Explain whether the oxygen containing ring has any aromatic character. The answer is yes. So let's see why. So we're going to have the resonance structure of that. And so basically, if you take these two electrons, move them there, and then take these electrons and give it to the oxygen, now you will have the following resonances. So you have a plus here on the oxygen and a lone pair. Actually, let me make that a little bit more elegant, like this. And I'm going to put the plus on the oxygen like that, and one lone pair. And this oxygen will have 6 electrons around it and a minus charge now. So you have a plus and a minus. Question: how many pairs of electrons can you read on this molecule? Hello?
I want to guess 8, but I feel like it's wrong.
Yeah, 8 is too much.
Do you not count all 3 pairs around the oxygen?
No, you don't count this. This is not part of the pi system.
Oh, then it's 5.
Yeah, very good. So it's 5 pairs. Was that you, Hannah?
Yes.
All right. So I'm starting to recognize my students' voices because I don't see the name here on the ticker. It used to, like, when you will speak, it will show your name, but doesn't do it anymore. 10 pi electrons. So this molecule is what? Aromatic, non-aromatic, or anti? What is it? According to Huckel's rules, 5 pairs is an odd number, right? So therefore he is aromatic. All right. Okay. So we get to the next problem. And I don't know, I think I mentioned it before. This problem, I took it from an MCAT test. So my oldest son was doing this problem, and after the test, he wanted me to explain it. And I thought, this is a really good opportunity to explain that to my other students. So here we go. Purines can be found in the nucleus of any plant or animal cell. Purine is an important base that is found as a component of DNA and RNA. Explain whether purine is aromatic or not. All right. So what do you see here? Notice that you have how many stock electrons do you read? First of all,
Is it 3 stock?
yes, there's 3 stocks. There's 1 there, 2, 3 pairs that are stock. They don't count. So let's put like a little X to those, and let's see the ones that count. So how many pair of electrons do you read?
Is it 5 again?
5 again. So we have 5 pairs. So we have 5 pairs. Total 10 pi electrons. So we have 1, 2, 3, 4, 5 pairs. All right. The ones in red are stuck. They don't count. All right. So let me write something here. So this molecule is aromatic. Wow, why am I getting that? This molecule is aromatic according to Huckel's rule. So in the structure of purine, only the electron pair on the nitrogen bonded to the hydrogen this one is part of the pi system. The electrons on the nitrogens that are part of the double bonds are stuck. Are stuck and perpendicular to the pi system. Both heterocyclic rings combined have 10 pi electrons. Why do they call them heterocyclic? Because they are cyclic and they have other atoms different than carbon. And so if you have sulfur, nitrogen, oxygen, phosphorus, it's considered heterocyclic. So both heterocyclic rings combined have 10 pi electrons. Therefore, the molecule of purine is aromatic. This is according to Huckel's rule. All right. So the next question is quite interesting, actually. Now, it says, explain which nitrogen atoms is, or parentheses, are more basic in the molecule of purine. And think why. Anybody wants to chat at this? Just think on your feet right now and try to come up with an explanation. Which one are basic? How would you approach this? Okay, think of this now. what will happen? This is how you think of basicity when it comes to aromatic rings. Now you know that all of these nitrogens are sp2 hybridized. Even this one will be sp2 hybridized. It looks like sp3, but it can do resonance. And if it can do resonance, then it's considered sp2 because it will be flat. It'll have three directions. So between sp3 and sp2, you choose the lower hybridization mode, which will be sp2. All right, and that's because it can do resonance. Now, what will happen if I put a proton here and make this plus? What will happen? So if that nitrogen is acting as a base, it has the property to deprotonate. What will happen? Do you win or lose aromaticity? Anybody? Huh?
You say that again.
Okay, what if I protonate here on this nitrogen and I put a proton there? So it's a base, so let's pretend that nitrogen is a base. Do I lose aromaticity if I take these two electrons out?
Yeah, because isn't it sp3 carbon then?
Exactly, you will lose aromaticity. It becomes sp3 nitrogen, and so then you'll have 2, 4. You have 8 pi electrons, so that's not good. So that is your least basic nitrogen. So what if I put a hydrogen here? Would I still keep aromaticity? Or here? Or better yet, here? I'm trying to erase that lone pair. Like that.
Do they all become sp3?
They all become, no, they're still sp2. They're flat. Flat as the tortillas that I'm about to eat as soon as I finish this class. Yes, they're flat. They're sp2. Notice that you still have 1, 2, 3 directions. And before, you have 1, 2, 3 directions. And it's stuck. Those 2 electrons are stuck. So, this is how you determine basicity. Also, without looking at the pKa's, because there's no protons here other than this one that can be taken out. And this proton happens to be very basic. So you have a high pKa. So because if you take this proton out, then it makes it worse. Now we're dealing with, well, it still be aromatic, but you have too much electronic repulsion there. So which one are the most basic nitrogens? Anybody? Based on what I just explained. Nobody dares to say anything? All right, let me write this down. The lone pair of electrons in the nitrogen bonded to the hydrogen is part of the pi system. These guys are part of the pi system. You don't want to distort that. If you add a proton there, that nitrogen will become plus. Then we're dealing with 4 pairs of electrons. Therefore, it will be 8 pi electrons, so that will be anti-aromatic. So you don't want any of that. Now, if protonated, purine will lose aromaticity. And that nitrogen, like someone says, who was that someone who said that nitrogen was sp3? Who was that?
Virginia.
Virginia Willis. Very good, Virginia. Thank you. That nitrogen will become sp3. The other 3 nitrogens, the ones that are stuck, the 3 nitrogens, lone pairs of electrons, can be protonated. Meaning acting as a base, and will not affect aromaticity. Therefore, all those will be considered basic nitrogen atoms. All of those. All right, makes sense? So protonating here, or here will not affect aromaticity. Therefore, those are your most basic protons. Later in next semester, you will also learn about pyridine. Pyridine looks like this. Has a lone pair. It's an excellent base because it's non-nucleophilic. And in the presence of a proton source, let's say you have this, it's an excellent base because it deprotonates. It doesn't lose aromaticity, and it doesn't go and act as a nucleophile on your reaction. And then from that, they call this base a proton sponge, because you can just grab a proton anytime you want it, and it doesn't do anything else on the reaction. So it's an excellent way of deprotonating undesired acids that are formed in the reactions. But we're going to learn this next semester. So I just wanted to give you a little extra there. All right. Any questions up to this point? So this kind of word problems really will test your brain, honestly, because you have to think about these things from that, the problem wants you to figure out how to solve this without much help, just a bunch of nitrogens and electrons. But that's what we're up against. So I'm trying to give you everything that I know in terms of aromaticity. All right, let's do the second part of this chapter, which is going to be devoted to the Diels-Alders. Now, I have a lot of Diels-Alders problems here, and I made all these problems to give extra practice to my students. I don't know if I necessarily want to cover them all, but we have time. So I worked on the homework for chapter 8 last night, and it's ready. I just had to submit it, maybe eliminate a few problems, because basically I went through the whole thing. There were like how much was that? 247 problems for this chapter. I narrowed it down to like 50, but I think 50 is too much. So I'm gonna trim it down to maybe 40 something, because I want to give you practice, and some of them are really quick to answer. So like you just click on a multiple choice question, and other ones you have to think. So you have a variety of it. But like I said, this book is great. I like it, but in certain areas it's kind of short, especially when it matches the homework. The homework comes from Pearson, and this book is from Pearson, and it really doesn't explain the Diels-Alders much. And this is an awesome reaction, but I'm going to teach you everything I know about the Diels-Alders, because I was able to figure out how to deal with it. Let me see. Give me a second. Let me get my USB. I'll be right back. So before I go over the Diels-Alders, let me take a walk through my recordings. Let's see. And I want to show you the model that I use. It's funny how these books, they just give you this stereochemistry, but they don't explain you why and how you get there. And they expect the students to complete them and know how to predict stereochemistry. Now I'm gonna teach you the right way, because everywhere I've seen these books, when it comes to Diels-Alders, they expect you to predict stereochemistry. So we're going to learn how to do it. So in my recordings, I mentioned that the Diels-Alders only works when you have an electron donating diene. This is your diene, and it's electron donating. You have an electron donating group. It works with an electron donating group or without an electron donating group. But it will not work if you have a diene and an electron withdrawing group. Like if you didn't have this group, it'll still work. But if you have an electron withdrawing group here where this group is, then the reaction will not work. Likewise, the dienophile, it'll work if it's only the double bond, if it's neutral, or if it has an electron withdrawing group. In this case, we have an electron withdrawing group. How do I know this is an electron withdrawing group? Because it has a carbonyl group. And a carbonyl group is right here. Notice that the oxygen is partially negative, the carbon is partially plus. That plus on the carbon makes it electron deficient, meaning it's electron withdrawing. So it will attract electrons because it's plus. All right. But if you have an electron donating group here, it's gonna hinder the reaction because it's not going to. You're gonna have opposite electronics. So basically, you want an electron donating group so that your electrons travel like this to form that ring. So I'm gonna put that like this. Yep. And so the conditions for the Diels-Alders is that you have an electron-rich or HOMO diene interacting with an electron-poor LUMO of the dienophile. It makes sense. So if you have your diene electrons in the HOMO will be, this will be the highest occupied, and you want to transfer that to the LUMO. So here's the diene, and here will be the dienophile. This is how, in terms of molecular orbitals, these guys can interact. And so that's what we're looking for. We're looking for that interaction to make an electronic flow. All right. So then most books will just say, okay, and then you get this group here down and this group here down if it's endo. And basically forces the students to memorize, oh, if it's endo, it's down. If it's exo, this group will be up, but the other one will be down. And so it's all memory. And although I think I have a good memory, which I'm not bragging about it, I don't like using it. I like to analyze things, because honestly, if I had to teach biology, I wouldn't do it, because it's all memorization to me. And that's why I like chemistry, because I can stand on my feet and think about a topic and try to solve it. And I guess that was how I was trained. I guess most chemists are trained like that. And we get drilled by professors when we are, getting our advanced degrees and stuff. But I like it. It's better. It gives, if you can analyze on a test, it gives you a better advantage rather than if you are unprepared. Like, for example, 2 questions that would require pure memorization, right? So I'll take that anytime if I can. But for something, but organic chemistry, honestly, you have to be both. You have to be good at both. You have to be good at analyzing as well as being able to have a good memory. All right, so we're gonna use this model. I did some search and came up with this, and basically here are the two options. So we're going to organize we're always going to put the dyene on the top, and right underneath we're going to put the dyene file. Notice the group C and D are facing inwards, because now there is what is called a secondary orbital overlap between C, the p orbitals in C, with this orbital that is right here. You will see it better on the next slide. And so that's the trick. That is the endo. That's why the endo product is more favorable. The exo is actually easy to deal with, but nature doesn't like it like that. So most likely the endo is usually like in the order of 7:3 or 70:30, up to maybe 90:10 most of the times. So the endo is the favorite product always. Notice that A here is always going to be down. Whether C, if it's endo, it will be down, but if it's exo, it will be up. And likewise, D will change. So we're going to learn how to come out with this and keep the stereochemistry of that other component. So this is fascinating to me. All right, so this model here tells you how to start drawing this. So first, imagine you draw a cube, and in the cube, you're gonna put your dyene on the top, and you have groups A and B shown there. You also have some electrons, some hydrogens that are like this. Right, we're not gonna draw those yet. If it's like, if they're pointing in like that, they're gonna be up. So initially we're going to avoid any hydrogens, but we have to imagine they're there. That's really important. So we don't draw them, so we don't cluster the image of the model too much. So the next thing is we're going to draw the dyene file underneath, inside. Like imagine that this group here is a drawer, and you are opening the drawer, and then you're going to push it in to close it. When you push it in, it'll be lined up as a box with the entire drawer. Understand? So this pi or p orbital, sorry, it's overlapping with the one here on C, and so this overlaps, gives it a solid stability to this endo approach. So I'm going to delete that so we don't have that. And then the molecule does what is called a concerted electronic movement. So notice that the double bonds are going to move. And so this interaction right here that is dotted will become a bond. Each one will produce a sigma bond. And so when it's ready to do it, I'm going to delete this so that I can show you. So this double bond here moves. Oh, let me get a better color. Yeah, let's use red. This double bond will make this double bond here will make that bond dotted. This one will make a pi bond there, and this one will break and make that bond there in red. And now you have, these are your new bonds. 1, 2, 3. That's what you made. All right. And so then take a look at what happens to the atoms attached to this, what I call accordion. This, so basically, this is a 3D model, and then notice that A is flat, pointing up, and so is B, and then C and D are inwards. So the next thing we have to do is add the hydrogens, and we will add the hydrogens. Notice that they're all going to be sticking up towards us. Unfortunately, I cannot show you with my hands, but imagine, I want you to now visualize this, and I want you to push this carbon and this carbon down to make it flat, going from 3D now to 2D. And you're gonna see that when you push that, like imagine you have like your hands tied up with both fingers, like if you had your fingers, maybe I'll show you with my camera. Imagine you have this like that, and now you're gonna push down like that. Can you see it with can you see my hands on the camera? So right now you're like looking at that like this. I call it like the accordion, and I'm gonna push it down like that. But what you're gonna see is the top of my hands. So you're like this, and now you flatten it down like that. And that is what creates the flat molecule here in 2D. And now notice that A has been pushed back, B is back, and so is C and D. They're all down. The hydrogens will be all up. All right? And so that's how we're going to predict the stereochemistry of these awesome molecules. All right. So we have this model. What we'll do, we're going to start with these problems, these two reagents, and then depending on what I ask you, if I ask you write the endo product, you will write this one, or if I said get the exo product, and then the homework will be like that too. There's one problem that I ask you for the exo. Then you do your exo approach, and then you get your exo product. It's gonna be really cool. Extremely fun. All right. And so here, notice that we'll do the same thing. Here we are moving these electrons around. Once we have the right approach, we move this double bond here, makes this bond right here on the right side. This pi moves over here to make another pi, and this other pi forms a sigma. So in total, you're reforming a pi, and you're making 2 sigma bonds. That is the Diels-Albers. Notice that this is a 4 plus 2 cycloaddition. You have 4 pi electrons on this side competing and merging with 2 pi electrons from the dienophile. So 4 from the diene and 2 from the dienophile. All right. What else can I say? I'm gonna leave those dots there. They look cool. All right. Yeah. So I think I talked a lot there, and I don't think I left much room here. It's 8:50, so we're going to continue with this next Monday. One more thing, the milestone milestone 3. No, is it? Yeah, milestone in time 3. It's going to be next Friday, October the 30th. So I don't know if I can fit in a quiz about this. Maybe I'll fit it in after the exam. I don't know. You would prefer it before or after, you think? Because if I practice a few, if I practice a few of this, those others Monday and some on Wednesday. No, I think I'd rather. If we're gonna have a quiz on this, it'll be after, I think, because we need more practice. And practice will make perfect. And then we'll cover as many as we can. But then I'll leave some for you to practice on your own, and then I'll post the key. All right, I'm gonna stop right there. Have a wonderful day, guys.